So I have found in the past that implicit differentiation really gives people a lot of trouble. So I thought maybe I would record my solutions to maybe one of the examples and one of the checkpoints to give you a better idea or maybe some more guided practice on how to deal with this. So one of the important things to remember about implicit differentiation is that y is in fact a function of x, and it's always a function of x. So no matter where it appears in the equation, it's always a function of x. Now, when I'm taking the derivative of something, so let's say, for instance, I have a really simple polynomial like y equals x, okay? When I take the derivative of this, I'm going to apply the operator d by dx. And remember, an operator is just something that gives me a direction, an instruction. It tells me what to do. Now, I'm going to apply this to both sides of my equation. Okay? So on this side of the equation, the right side, the thing that I'm taking the derivative of is just an x. And so I can take the derivative of that. It's pretty simple. I can take the derivative because it's an explicit expression in terms of x, and that's going to be 1. But the problem is that on the left side, my y is not an explicit function of x. It's a function of y. And that means I need to write this whole thing to remind myself that y is a function of x and I have to take its derivative. So if I had, for instance, y squared was equal to x, and I was going to take the derivative of that, well, the derivative on the right side is pretty easy. It's just going to be 1. But on the left side, what I really have is the chain rule, okay? My outside function is the squared, and my inside function is the y. So I have 2 times y. But remember, when I'm doing the chain rule, if the thing inside the function, the outside function, is not just an x, then I have to take its derivative. So the derivative of y is dy dx. So the rules when we're using implicit differentiation is that if my term is just a function of x, I take the derivative just the way I used to. If my term is instead a function of y, then I have to basically apply the chain rule and remember that my last step is to take the derivative of y with respect to x. And if I have mixed terms, say I've got x times cosine y, then what I need to do is apply the product rule or the chain rule or the quotient rule, whatever it is that I need to be able to take those derivatives. So I want to look at example 3.6.9. I know that they go through the steps in the textbook, but I just felt like it would be good to go through it together. So I need to find dy dx of that expression. So my first term here is 2 functions that are multiplied by each other. So I'm going to have to use the product rule. So I'm going to take my first term, and I'm just going to write it again, and that's x cubed. And then I've got sine of y here. Okay, and again, that's a composite function. My outside function is sine, my inside function is y. So the derivative of sine is cosine of y. But then, because the argument of my trig function isn't just an x, I have to use the chain rule and take the derivative of what's inside. So that's going to be multiplied by dy dx. Now, I do the second part of the product rule, which is to take the derivative of the first term, 3x squared, multiply it by the second term. All right. And then I take the derivative of y, which again is a composite function, even though it doesn't look like it. So it's really y to the 1. So my derivative would just be 1, but it's not an x. So I have to take the derivative of what's inside, which is that y, and have dy dx. The right-hand side is a lot easier. It looks more familiar to us. The derivative of 4x plus 3 is just going to be a 4. Now, we just have to do some algebra. We're going to treat dy dx as a variable. So I'm going to factor out dy dx. So I've got x cubed cosine y plus 1. I'm going to move my terms that don't have dy dx and then to the other side. So that's going to be 4 minus 3x squared sine y. And then I'm just going to divide both sides by this so that I can have dy dx by itself. And this probably looks a little weird because your answer is a function of x's and y's, but sometimes that's just the way it works. And this allows us, implicit differentiation allows us to take the derivative of functions that are more complicated. It can't be easily expressed as y equals something that's only a function of x. So look for another example further on in the reading guide that has a video to go with it, and I'll see you in class. Thanks, bye.